Hello everybody, my name is Danielle Feigl, and today we're going to be going over the third problem on homework 2 from the class Transport 2. The problem involves a closed capillary system with H2O on one side and D2 on the other side, equal volumes, and then they're going to be diffusing together. And in this third problem, we are going to be sketching some graphs that will describe different components of the system at different times within the system. So if we go ahead and look at the first one, H2O is going to be listed in red, and D2O is going to be listed in blue. I'll draw the capillary out really quick just so that we can all see what we're looking at here. Before they begin at about t equals 0.1 second, this is about what the system would look like, equally dispersed between H2O and D2O. At 5 or 0 to 5 is H, and 5 to 10 is D2O. So looking at our first set of graphs here, we have the mass concentration in kilograms per meter cubed. In our first problem, we defined the mass concentration as the 1/2 of the density of the of each component. So since the density of water is 1,000 kilograms per meter cubed, I listed that first point at 500 kilograms per meter cubed, and D2O is 1,110 kilograms per meter cubed. That would be the density for that one. So similar, I divided that in half. And since this is the very beginning of the system, these mass concentrations will be uniform throughout the whole capillary where they are encompassed. At the end, they should have reached equilibrium, so their mass concentrations should be half of what they initially were and equal and constant throughout the whole capillary tube. And then somewhere in the intermediate, there should be just a flowing somewhere in between, showing the transition. I think it's important to mention that in each of these graphs, the integral under each curve, red and blue, should remain the same throughout the three graphs. It may not be exactly reflected in the way that I'm drawing them, just because I can't draw perfectly, but the area under the curve should remain the same. In the second set of graphs, we are working with molar concentration in the terms of moles per liter. We calculated that in the second problem, and I believe that one was 1/2 of density times or divided by the molecular weight of the system. And so both of those ended up coming out to about 27.7 moles per liter, because 1,000 liters is equal to 1 meter cubed. So at the beginning, similarly to the mass concentration, that's just going to be that 27.7 number. Both of these are really close together, so they look at that like they're starting at about the same points. And in that middle where the boundaries meet, it goes down to 0. Exactly how it was done earlier with the mass concentration, at t is infinity at the end of the system, it should have reached equilibrium, and the mole concentration should be half of what it was at the beginning at all points throughout the capillary tube. The mole concentrations should be the same. And the number calculations are just slightly different, but they should be about the same. since they're equal volumes and stuff. Next we have the molar diffusive flux graphs. We know that the molar diffusive fluxes that was originally given, they are equal and opposite. Since D2O is on the right hand of a capillary and moving left in the negative z direction, that one will be the negative 2.78 moles per meter squared times seconds. And that will happen right at the boundary. That's where the highest molar diffusive flux will occur. And then these are pretty sharp peaks, so that since there is no really there's none of the other material in the other areas to transfer over, so those peaks should be pretty sharp. And then in the middle, of course, the maximum molar diffusive flux will be lower, and it will have spread out so that there is at least some molar diffusive flux at each point within the capillary tube. And then by the end, it will all reach 0 once it reaches equilibrium. The final set of graphs deals with the total molar flux, which is what we calculated in problem 1 to be negative 5.56 times 10 to the negative third kilograms per meter squared seconds. So just like before, that's going to be a pretty sharp peak because it's going to be, it's just going to have the quickest molar flux, total molar flux right at that center point. And then once it reaches equilibrium, it should be equal to 0. So then in between, we have this less sharp peak where the total mass flux is non-zero. And that is it. That goes over all the trends covered in problem 3. If you have any questions, feel free to post them in the comments below, and have a great day.